So today we will learn about cycles, say long cycles. So we learned that in undergraduate graph theory, we define the spanning cycle as a Hamilton cycle or Hamiltonian cycle. So some people say Hamilton cycle, some people say Hamiltonian cycle is a spanning cycle in a graph. And we say a graph is Hamiltonian if it contains a Hamiltonian cycle. And we run several theorems. One of them is a Dirac theorem. Prove that if we have a graph G whose minimum degree is at least n over 2, and say n is at least 3, then G is Hamiltonian. And this theorem is sharp as, we can consider roughly n over 2 minus 1 vertices here, n over 2 plus 1 vertices here, and then take the complete graph between them. Let's just say n is out here, otherwise we take floors and ceilings accordingly. Then it's easy to see that this doesn't contain any Hamiltonian cycle, but its minimum degree is 1 less. So this condition is best possible. And there are generalization of this theorem. Oral theorem says that instead of this condition, if we have the sum of degrees of two vertices at least n, or all non-adjacent, UV, say U and V are different, then G is Hamiltonian. Again, n is at least 3. And also there is Quaternion theorem. Says that again n is at least 3 and G has degree list T1 to say Tn. And for each I strictly smaller than n over 2, either Ti is bigger than I, or T sub n minus I is at least n minus I. For all I, either one of these happened, then G is Hamiltonian. So in undergraduate graph theory, we proved this by using the concept of closure. So essentially how we prove it is that if we have two vertices U and V, and if they are not adjacent and their degree sum is at least n, then we add an edge. And we keep add an edge until we cannot anymore, then we say that that resulting graph is the Hamiltonian closure of G. And we prove that G is Hamiltonian, and if and only if its Hamiltonian closure is Hamiltonian. And we show that if this condition holds, then its Hamiltonian closure is complete graph. So which is kind of modern version of the proof, but the classical way of proving, say, Dirac theorem is that we take a longest path. And in this longest path, if this is not Hamiltonian, then it's let's say it this way, okay? We have a longest path, and if they are adjacent, and there are vertex outside, then this condition actually makes sure that the graphs are connected. So you can find the edge between the cycle and a vertex outside. Then that yields a longer path. So which ensures that I mean, there is no edge between the two endpoints in the longest path. And now this is longest path, so both of them does not have a neighbor outside. In that case, we get a longer path. So they have all neighbors inside, but as soon as we have two vertices, so V1 and say VL, V1 has a neighbor here, Vi plus 1, and VL has a neighbor Vi, then we can get this cycle. And again, by the fact that graph is connected, we can find the vertex outside which has neighbor in one of the vertices here. And this cycle with this edge again yields a longer path. So those are the basic technique how we prove the, Dirac theorem or Euler theorem. And actually at the moment I don't remember how we actually adapt this to prove the quatile theorem, but that's the basic idea to prove this, theorem. And we can actually, not only talk about the spanning cycle, but we can instead ask, about the longest cycle. Even if some graphs are not Hamiltonian, we can still, ask a question that what's the longest path, longest cycle in here. Even if that doesn't contain a spanning cycle, does it contain a cycle with length m-1 or m-2? So let's define the length of a longest cycle in G is circumference. Say, let's write C of G is the circumference of G. Then one of the typical extremal type question we can ask is that what's the relationship between the number of edges and circumference? If we have at least that many edges, then can you say something about its minimum circumference, minimum possible circumference? For example, if you have number of edges is at least n over 2, then circumference is of course, n. We can actually show that, n-1 choose 2 plus 2 implies, circumference n. So for more generally, what's the threshold? What's the number that ensures this circumference at least, s or bigger than s? So first theorem we want to prove is regarding this. So this is Eridi-Shkreli theorem. So for S at least 2, if G is on m vertex graph with say more than S times n minus 1 over 2 edges, then C of G is strictly bigger than S. So actually this is sharp, meaning that this is best possible, meaning that there is just a graph with exactly this many edges, while the circumference is not strictly bigger than S. Say, assume S minus 1 divides n minus 1, and you take copies of KS. So this is copy of KS, complete graph on S vertices, and this is another KS, And how many copies? n minus 1 choose K minus S minus 1 copies. Then here we have S minus 1 vertices, S minus 1 vertices, S minus 1 vertices, and this many copies. So altogether n minus 1 vertex and one more vertex vertex here. So total, this is n vertex graph. And here, what's the number of edges? Each copy has s times s minus 1 over 2 vertices. And then number of copies is this much. So you get exactly this many edges. But the circumference is s. So you cannot get, if you want to have a cycle with length at least s plus 1, you have to start at some part and then you have to go to other part. Then there is no way that you can come back unless you want to use this vertex again. So this shows that, this is sharp. So now we want to prove this theorem by Eredish-Carlyle. And how do we want to prove it is, again, using the similar idea as before. We want to take a maximal path with the longest length. And now what we want to show is that if we have some h between p1 and say k, then this is length L, longest. And what can we know? If this k is bigger than s, then we are already done. This already gives us a cycle of length L is s plus 1. So most of the neighbors of p1s are on the first part. So so most of the neighbors are here. And we want to also use induction. Say, also what do we know is that if this vertex has again neighbor outside, which is kind of far from here, then this can give us some long cycle. So this shows that the vertices inside here does not have neighbor which is too far from here. So it shows that the vertices in here all have somewhat smaller degree. So intuitively, with this information, what we want to do is we want to cut these vertices out and then show that in the remaining graph, we have a larger number of edges. The density goes up. Of course, n goes down, but with the new n, this condition satisfied in here so that we might find the cycle here. So if we don't have cycle here, that means this is sparse. So that means, there is some vertex with high degree. So we either have, cycle of this type or cycle of, cycle of this type. So with that on mind, it's convenient to actually not just take a path with the longest length, but also, longest path which ensures the largest degree on this P1. So that's the basic, in that case, if P1 has the largest possible degree among all longest paths, then if you take, say, this path, then this path has the same length and this is the end, so we can put some upper bound on the degree on this vertex. So which, helps us to upper bound the number of edges incident with these vertices. So with that idea, we can start the proof. Let's say we use induction on n plus s. And we may assume S is strictly smaller than N. Otherwise, because, if N is S, then this is N choose 2. There are no graphs with more than that many edges. So we can just assume S is strictly smaller than N. Then, what do we have? The induction hypothesis is that circumference of G is at least S. What's the induction hypothesis? So we consider N, same graph with N, and we consider S minus 1. This is smaller, so we can apply the induction hypothesis. Then this has the same condition, which is strictly bigger than S minus 1, M minus 1 over 2. So it says that the circumference is strictly bigger than M minus 1. So we know that its circumference is at least S. So suppose it's exactly S. If this is S plus 1 or above, then we are done. And we also assume G is connected. If this is not connected, then you take a component, which satisfy this condition with the n prime vertex component, which satisfy this with the n prime here. There must be such a component. Otherwise, you can just add up the number of edges and check that that must be satisfied. So we assume G is connected. As we plan, we take among all longest paths in G, choose a path P which maximizes the degree of the first vertex, say P1. And let K be the degree of this vertex P1, and P be P1 to PL, with say L is at least S. Because we assume the circumference is S, we know that there exists a path with length S. As P is chosen among the longest paths, it has length at least S. So let's say this is P. And we note G is connected. P1, PL is not an edge, because otherwise we have a vertex outside, and connectivity implies that there must be a vertex outside which has neighbor in one of these vertices. Then this yields a bigger path, longer path. Otherwise, an edge leaving PP, here is a longer path. So let W be the vertex is Vi, where Vi plus 1 is the neighbor of V1. So for example, if we have this neighbor, and this neighbor, then this is in W, this is in W, this is in W. Because V2 is satisfied this, so V1 itself is in W as well. So it's a right previous vertex other than from the neighbor of V. And then we know that W has size K. And because all neighbors of P1 must lie in the vertices of this P. Otherwise, we get a longer path. Also, as the circumference of G is at least S, at most S, we have that this W is lies in first S vertices. Otherwise, we get a longer cycle. So, as I mentioned before, now what we want to show that these vertices in W has not much, degree. So given Bj in W, we can form, say, path P prime, which starts with Bj, and Bj minus 1 until to B1, and Bj plus 1 to Bl. So we can form this path. This is also a path having the same length as P. So this is P prime is another longest path. So neighbor of Bj is again lies in this path, because otherwise in this path, if we have a vertex outside which is neighbor of this, then this gives us a longer path. And also Bj has degree at most k, because that's how we take among all longest paths, we choose a path maximizing the degree of the first vertex. Again, in this new path P prime, this is the first vertex, so it must have degree at most k. Also, furthermore, no Bj in W has a neighbor Pt with, say, T bigger than S, because otherwise adding Pt Vj to P prime, here's a cycle of length more than S. Because if this has, Pt with T at least S, then you get this cycle, which has length T, which is bigger than S. So now let's say capital G be the first S vertices. Then what do we know? For each Bj in W, we have its neighbor lies in G. Then the summation of all degree in W, it counts edges in W twice and edges in this cut W and G minus W. So edges between W and G minus W once. So W is incident with at most say half times summation of degree plus the number of edges between W and G minus W. This many edges. And what do we know? That is actually half times K. So each of them is at most K, and then W has size K, so K square plus W has size K, and then G minus W. W all lies in G, so that has size S minus K. So K times S minus K, which is at most Ks over 2 edges. Then G minus W has more than Sn minus 1 over 2 minus Ks over 2 edges. So Sn minus K minus 1 over 2. More than this many edges. And it has n minus k vertices. So this is a smaller graph. Since we are doing induction on n plus s, so n decreased while s is still there. So induction hypothesis is G minus W has a cycle of length bigger than s. Thus, circumference of G, that cycle also lies in G. So this is strictly bigger than s. So this proves the theorem. So this shows this answers the question that how many edges ensure the cycle of length s, or strictly bigger than s. And also we can ask a question on this minimum degree condition. So what minimum degree condition guarantees cycle of length n minus 1 or n minus 2 or certain number? So there are some long cycle version of Dirac theorem or Euler theorem. So long cycle version of Dirac theorem says that if we have a two connected graph G, then it has a cycle of length at least minimum n or 2 of its minimum degree. And we add these two connected condition to eliminate the case of this. Say this is KD, and you add all edges between this B and D. Then minimum degree is D plus 1, while the longest cycle here has length t plus 1. So in this case, this doesn't hold, so we add these two connected condition to ensure that this holds. Anyway, so also there is version for the Euler theorem. And to prove those two, we want to prove the following lemma. So lemma by Bondi. If P1 to L is a longest path in a two connected graph, with n vertices, then circumference of G is at least the minimum of n, or degree of B1 plus degree of BL. So in the next lemma, we will prove this Bond's lemma.